I mean, you can appreciate that, if you start with this expression in n going to infinity limit, this you can take it to, I mean, in the limit, this is just, the denominator is just 1, and so you end up with this expression. Clearly, this expression, if p is greater than q, and in fact, if I is sufficiently large, this number can also be small, and that is the probability of A winning can still be very high. Okay, so let me then start preparing for today. Yes, okay, maybe I'll just summarize what we have done in last class. I'll just start the recording. Recording is going on, right? I think. I suppose. Once. Yeah. So, I mean, very quickly, just to go through what we have done in yesterday's class was, we started with this problem of this, this game of gambling, gambler's ruin. So basically, a gambler plays a game where at each time the gambler can lose certain capital or they can gain a certain capital. And just give me 1 second. Yeah, and then what we had done was we had mapped this problem onto this random walker, and we mapped the problem to random walker in 1 dimension, and then with the boundary condition that the probability at x equal to 0 is 0 and probability at x equal to 1 is 1, and then we assumed, so for this, then we wrote down the recursion relation, and then we assumed a solution of particular form, and then when we obtain the solution of that thing, we obtain the basically the expression of this probability of A winning the game and analyze the different limit. So whatever we did until now was analytical. And now what I'm going to describe today now is how you are going to basically, what are the steps, how you are going to use Monte Carlo simulation techniques that I have already discussed for this particular problem. So I'll just outline those steps. That's what I'm going to do. So I'll just try it. I mean, so basically what I want to do is Monte Carlo simulation for generating the probability distribution, that is the probability of A winning the game, starting from a given I. Okay? So that's what we are interested. So this is the aim. So that means I want to, using this Monte Carlo simulation, I want to actually find out the P of A for a given value of I, N and P. Okay, for a given I, N and P, I want to find it out numerically using Monte Carlo simulation. So that is the aim of the thing. So here the first step is that when you are writing the code, the step 1 is you have to provide this, read this inputs. And what are your inputs? Inputs here are, that means you have to specify I, which is the initial capital of the gambler, or in random walk language, it is the initial position in the in the 1 dimension where your random walker is starting. So that's the initial position of the random walker I. So that you have to specify. Then you have to specify N. In terms of the gambler's ruin problem, there is a total capital which is fixed. That means if you take the total capital of A and B, that number is a constant. So that you have to specify. that between A and B, what is the total capital? Or in the random walker language, the random walker is doing this random walk in between x equal to 0 and x equal to n. So you have to specify what is that capital N. So that is this one. The third one basically relates to that if you are starting at position I for this random walker, then it can hop to the neighboring side on the left or right, and the hop to the side on the right happens with probability P. In terms of gambler, it is the probability with which when he plays one mini game, the probability of A winning, 1 rupee more when he plays one mini game with B. So that is your P, and this you have to specify. And when you have specified P, like I mentioned, the probability with which he loses money and goes from I to I minus 1, that happens with probability 1 minus P, which we call as Q. Okay. So first part is, of course, we have to read this inputs that are required. Then second step is you call a random number. Of course, call a uniform random number. So this is the second step. And let's say this random number, you just give it some variable name x. Okay. And remember, when you're calling from this uniform random number, this x would lie between 0 and 1. So you call this uniform random number. This is your step 2. Now now you try to understand that what is the meaning when you say that initially when the initial position. So I should mention, okay, just so that we don't confuse the variable, let us name this variable, because I am also using x to signify the position of the the random walker. So let me call this uniform random number r, so that there's no confusion. So r must lie between 0 and 1. Initial, so when I read the input, I forgot to mention your initial position. That is nothing but I. This is your initial position or the initial capital of A that A starts with at the beginning of the game. So now, second step, after you have called the random number, what you have to see is if this random number. So this is, let me call it step 3. If your R is less than P, then what you do is, so that means this move is successful. So this is also called a Monte Carlo move. So the step 3 in the language of Monte Carlo, you make a Monte Carlo move. That means you call a random number. And if that random number is less than P, so P would be what kind of value? P would again be, like if it's an unbiased random walker, that P, in that case, P would be half. So that means if you call a random number between 0 and 0.5, then your move would be successful. Or in other words, this I, that means the new position, instead of you had started initially with x initial, whatever you had given, it will go to I plus 1. So if this is true, then your x would basically become x plus 1. Okay. And similarly, if the other condition, that is else if R is greater than P, then your x becomes x minus 1. That means you are basically mimicking this process of this random walker or this gambler hopping from I to I plus 1 with probability P, and similarly also mimicking the probability with which it is hopping to I minus 1. This point is really, from conceptual viewpoint, you should really understand why this would be true. You can just think about it. Finally, if I had looked at what is, how this particular step is actually able to mimic this probability P and Q. This is kind of obvious, but let us again, just to emphasize this, you must realize the following: that had I plotted P versus this P of getting this random number r, and let's say this axis is x. Yeah, okay. So now this is how the uniform probability distribution would look like. That means it would lie between 0 and 1, and all of this numbers between 0 and 1 appear with equal probability. So when you are saying that, when you are putting the if condition that, oh, when probability is less than p, I will make the transformation from I to I plus 1. To give you an example, let's say p were equal to 0.6 or let's say 0.75. So say 0.75 would be somewhere here, right? So if you had called a random number in this line between 0 and 1, in any case, the probability that that random number that, I mean, you are sort of asking the question, if you had called a random number from a uniform distribution, what is the probability that the number that you have called is less than 0.75? That means all this area would correspond to the probability of getting a number less than 0.75. So the random number does that, and in the process, effectively what you are doing is you are generating the probability of small p and small q respectively. So when you say that, so that means your move is successful or I becomes I plus 1 whenever the number is less than 0.75, and it actually happens with the same probability with which this uniform random number is less than 0.75. And similarly, if that number happens to be greater than 0.75, the other thing happens. That means the other event is that I becomes I minus 1. Is this point clear? Because this is a central point. Any Monte Carlo method, it relies from this first step. Whatever, even the different other problems that you do, you are making use of this property of uniform random number to basically mimic or generate this individual step probabilities that you are seeing here. Okay, so this is as far as the third step goes. And so when you do this third step, that means you're calling a random number, you are making the move. In the process, that means you are basically updating the position of this random walker or this gambler from I to its new position. So let's say this move was successful and your random walker is now in this new position. So when you are in new position, basically what you have to do is you have to keep on doing this. So after step 2, you update the position, you go to the new position which are given by this x becomes either x plus 1 and x minus 1, and then you check the following condition. See, you remember the game ends whenever your x becomes either 0 or n. So every time you start with this initial position x becomes x plus 1, you should keep on repeating this process. That means you keep on repeating steps 2 and step 3 and updating the corresponding positions x until x becomes either 0 or x becomes either n. So that I would call as the step 4. So step 4 is basically repeat step 2 and 3 until x is equal to 0, or that means I is equal to 0, or x is equal to 10. Okay, when x becomes equal to 0, so let me call that as step 5. So let us look at this time. See, remember, if x is equal to 0, what does it mean? That the gambler A, who had started with this initial capital I, has completely lost the money, and that's why the game has finished. And in this case, the particular event is that he has lost the game, right? That is one possibility. The other possibility is that he keeps on, repeating the step. It starts with some initial capital and then it increases, decreases with this respective probability P and Q. And you end up in a situation where the final position X becomes capital N. So if X is equal to 0, you basically go back to your, step 2. So if X is equal to 0, just go back to step 2. That means you again call a random number and keep on doing this. If the other thing is true, that means if X is equal to N, then you should have another counter. That counter basically measures how many times your event that A has won the game, starting with some initial value, that has been successful. So if that has been successful whenever this particular condition is satisfied, and when this particular condition is satisfied, you have some another counter. Let me call it NW. So this NW counter will become NW plus 1. Of course, I should of course mention that NW is essentially your NW initially. You should keep that counter starting before you enter the do loop. You should have it as 0, and then you start from 0. So every time so you keep on doing this step, right? So every time you play the game, then whenever you have this X is equal to N, this condition is satisfied, then you increment the counter of NW by 1. Okay, and you keep on. So I'm saying even in the first case, if X is equal to 0, that means you should have another counter which will tell you what is the number of times you have actually played the game. So let me define another counter. Let me call use some other variable. Let me call it M is equal to number of times an entire game is played. An entire game is played. So whenever any one event where you enter X equal to 0 or X equal to N, you should also increment this counter M goes to M plus 1. Okay. And finally, just going back to the definition of what is the probability of A winning the game, that means you are basically, what you are looking at is, you are, that means, playing this game M number of times. So this M you should think as the total number of ensembles that you are using to generate the probability. And by the very definition of probability, the number of ensembles, I mean of all the ensemble members, the number of time a particular event has been successful. Here the particular event just corresponds to the fact that A has won the game. And so when you play this game, n number of times, the probability of, I mean after all of this, so you can call it step 6, then you have basically, that means, yeah, so in fact I should say that apart from the 3 input that I mentioned, the 4th input is the number of times you are going to play, or number of ensemble members that you want to take into account. Typically M value should at least be 1000. In your simulation purpose, you should try at least like 1000, 5000 or 10,000. So you should take the value of M in your programming when you actually do. It should be at least be 1000, but maybe you can go up to 10,000. The moment you do for 10,000, you will see you will get more accurate result. But coming back to the problem in hand, what you are interested in is getting this probability P of I of, and that is nothing but this NW after you have done this n number of steps. The number of times NW is nothing but the number of times your final run has ended in the position X equal to N. That's when A wins the game, right? So NW divided by N gives you the probability of A winning the game. Related question is, you can ask what is the probability of B winning the game. It is just if you want to ask what is probability of B winning the game, it is just 1 minus B. Okay, so is it clear? So if you think of the structure of the program, there would be the following things. You would of course need to call a uniform random number, and then you would need 2 do loops. The inner do loop. So the outer do loop is where basically your do loop will run from 1 to a capital M number of times. That means if you want 10,000 samples, the outer do loop will run from 1 to 10,000. The inner do loop basically every time, that means every time you initialize the starting position of X to be I, whatever is the input. So that you have provided. And then it has to run. No? Inner do loop is like an indefinite do loop which stops whenever your I value is either 0 or I value is equal to n. And then you again go to the outer do loop, initialize and do the run. Is this step clear? The general procedure of how to go about what I just described, or are there any questions? Because we have to finally generate, I mean, this is just the starting point. I mean, as we go along, we'll see that the Monte Carlo simulations are more involved, but this is sort of the starting point. So you'll have to program this thing, whatever I told you. Additionally, so I'm going to tell that we are also going to discuss this question, that here we have generated the probability distribution of A winning the game. So for you, whether your Monte Carlo simulations are correct or not, the check is that from your simulations you'll get some number, right? So this is the numerically obtained result. You already, what we discussed over the last 2 days is the the analytical expression which we have derived from analytical arguments, and you have to basically compare the results of that analytical result with whatever you get from your numerics, calculate what is the error that you are making, etc., etc. For different values of P and Q. I mean, for the symmetric case when P is equal to Q. So you have to basically analyze all these different limits, make a comparison. So that would of course be part of your assignment. Another related question which you can do within using the same program. You don't have to write another code. You have to just slightly modify the program. And the question you can ask is, you can ask that, every time, just imagine every time you play a game, so you can associate a notion of time, right? That means, or basically the number of times you have to toss the coin, or number of times, I mean, what is a typical sequence? So if I look at it, you start with some initial capital I, and then there are this whatever, this I, let's say, is 25. And then from this initial position, every time you do this procedure, you are taking basically a step to the right or left. So it can be different sequence of steps, right? Left, right, etc., etc. And you finally, your last step is whenever you reach this condition of x equal to 0 or x equal to n. Now, every time, that means you are calling the random number, that means 1 unit. So every time you are doing this mini game, it is like as if 1 mini unit of time has gone, right? And you can imagine that, that event, this is how much, this itself is a random variable. That means what is the duration of the game? That it starts every time, of course, it starts with the initial capital of, let's say, 20. And first time you play the game, becoming from 20 to 0, it might have taken 100 steps. Second time you start with the same initial condition, because it is again a random process. The next time you play the game, instead of 20 steps, it might be 100 steps. Third time you play the game, it might be 50 steps. This number of steps is nothing but basically the duration of the game. So there is a duration of the game. And the important thing to realize is that this duration of the game itself is a random variable. And you can ask the question, what is the probability distribution of the duration of the game? Right? So you want to find out. So the question you want to ask apart from this probability of A winning the game is, so let me call this P of T, which is nothing but probability of duration of a game. Game, how we have defined that you start with some initial I, and the game basically finishes when you reach x equal to 0 or x equal to n. And the question we are interested in is, what is the probability of duration of the game? And you can ask related questions. So once this is, of course, you are interested in the full probability, but various statistical properties. That means you might be interested in what is the mean duration of the game. This is nothing but mean duration of the game. Similarly, you might be interested in the question, okay, what is the RMS fluctuations? That means this quantity. What is this? All this, so all these three things that I am writing down and all the other, in principle, other statistical properties. This I want to use again this Monte Carlo simulations to generate the entire distribution and find out these average values numerically. And the way to do about it is, whatever I told you describing the algorithm for finding out the probability of A winning the game, you have to proceed exactly all those steps you have to follow. Only additional thing is you will need an additional counter of time. So whenever when you are doing step 2, that you call a random number. So whenever you're calling a random number before making a move, that means before you are incrementing I to I plus 1 or I minus 1. So whenever you're calling a random number, basically your time starting from the initial time has moved by 1 unit. So just think of a clock. So the clock has moved by 1 unit. And then 1 unit of clock has moved. And then basically whatever, that particular game might end with x going to 0 or x going to n. And you record, so every time you're calling a random number, you increment the time by 1 unit. And whenever that a particular game finishes, you record that final time. So that means you should have additionally one more counter. So in step 2, after step 2, in step 3, basically whenever, so step 2 you have called the random number, right? Called random number R. And at step 3, so whenever you have called the random number R, you increment your time. So you should have some counter which is going to store t, and that counter will become t plus 1. And then step 3 is basically you move whatever I becomes I plus 1, etc., etc. Remember, in step 4, the game finishes whenever this if condition is satisfied, that if x is equal to 0 or x equal to n. Whenever this condition has satisfied, t would have taken some value. What you have to do is you have another array, again a one-dimensional array p of t, which would be incremented by 1. And when you increment it with 1, now you set t equal to 0 again, because you want to again play a new game. This time again you initially go back to the initial position of the random walker, set it to whatever is I, then the new game starts, and again you do this process of t becoming t plus 1. Again, whenever it reaches this x equal to 0 or x equal to n, you will have some particular value of t. That particular value of t, you again increment the array of that p of t by 1 unit. This way, what you are essentially are doing is, you are essentially actually getting an histogram. So imagine when you, and finally remember, you are going to play this game capital M number of times, right? You are going to play 10,000 number of times. For each 10,000 number of times, sometimes the total duration of the game might be 500. In other cases, it might be 550 time units. So you have to fuel this, but you have essentially collected that information in P of t. So all you have to do is just draw the histogram with appropriate binning, that whatever, so make a column, this is P and this is P of t. You have to, that means you have collected the data number of time, the time is between 0, and so you have to have some binning size, right? Between 0 and 50, 50 and 100. So whatever are the number of points in that interval, you have to collect, and that will give you basically the histogram, and you will, in principle, you will be able to generate the whole distribution of P of t. That is number 1. Second is, if you want to, for instance, the question we were asking is, what is your average value of t? That means every time you have a particular value of t, you keep on adding all the different times that you get for each of the individual ensemble members. add all of them, divided by capital M, and that by definition is the average value of P. So this is how you can go on to also find out the corresponding distribution, probability distribution of the duration of the games and the related quantities like average duration of the game, etc. Fine. So yeah, so I'll finish here as far as the aspect of how you do the Monte Carlo simulation for this random walker and related this gambler's win problem. So this is the step, and this is something that you would have to do in your assignment and later. Okay. Are there any questions? Because if you have any questions regarding this, please ask, because I'm going to move on to a completely new topic. And in fact, in afternoon also, we'll continue with that. I hope the steps are clear. And I'm just saying that, let me be very clear. See, one thing which I have told right at the onset of the course, that as far as debugging your program is concerned, that means, any syntax error, that you have to manage on your own. That I mean, it is expected that if you have done your quantum computer 1 course, that syntax you have to manage on your own. My job is to show you how to do the simulations using this thing, and that of course we can discuss wherever there is doubt. I'm going to clear that. But this you have to do the code on your own, and whenever the assignment comes, you have to do the code and find the result and submit it. So this is as far as this method goes. So that if you are any, please clarify it in any case. I'm saying today, or if you have, if you go through the method and you still are not clear, you can of course ask questions and get it clarified. But get it clarified soon, because whatever Monte Carlo methods that we are going to do, like the subsequent problem, are more advanced. It is much more subtle than this, and so you would, if you not clear with all this thing, then you will not be in a position to do the next one. So it is all these many steps that you have to take. So the level of difficulty is going to increase as far as the Monte Carlo method simulations are concerned. Okay, so if there are no questions, I will go to another problem. And remember that one of the things that I said was that we are going to look at examples of how you use Monte Carlo simulation method for non-equilibrium problems, non-equilibrium systems. So non-equilibrium, so in principle, what I am going to describe is first, so how we are going to span out the next couple of classes, that I'm going to describe a particular model which is a non-equilibrium model. So first I will actually develop the analytical, in fact what we'll call the mean field theory for that model, and how analytically you can get the various results that are of interest. And then after I have discussed that, I will describe how you have to, and which you have to finally do, how you perform a Monte Carlo simulation in order to get the steady state properties of that particular non-equilibrium model. Fine. So that is going to be the route for the next couple of class. And I mean, just to emphasize, so after we have done this non-equilibrium model, we would go on to an equilibrium model, which is the icing model, which we would again analyze and see how you use Monte Carlo simulation technique to do it. So today I'll just begin with, right now, I mean, since limited time, I'll just state the model, and then in the afternoon at 2 o'clock, when we meet again, we would proceed with the derivation of the model. So this model is called, so in shorthand, it is called PASSET, and this is shorthand for the actual name, which is called totally asymmetric exclusion process. And as we go along, it would become clear why the name is as it is. But first, I will pictorially represent this model, and again, this we would be discussing this model in 1 dimension. So again, it is a 1D model defined in 1 dimension, and So just like now that you're familiar with this random walker problem and the last problem, so consider a lattice. So this side is like, let me call this the first side, and this is your last side, which I call I equal to n. And so these are your lattice sides. So you have an n lattice points. Now these n lattice points starting from 1 to n, so there are n lattice points. Now imagine, so I mean, if you want to think in terms of physical terms, I mean, for instance, you in your solid state course, you're already familiar with the notion of lattices for describing solids. So then all this atoms, whatever they sit in this lattice positions, etc., etc. So all this. So now just imagine mentally that you have just a 1D kind of solid. You have this lattice points, and now, but it is different from the problems that you have encountered in solid state physics in the following sense. So imagine you have just one particle, and that particle can sit in this lattice sites. So any lattice site can either be occupied or they can be empty. And at maximum, only one particle, let's say, can sit in this lattice sites. So, so let's say if it, so if there is a point here, I will, if there is a particle sitting in this lattice site, I will denote it by cross. Otherwise, I will just write, blank. So this is like vacancy. So if there's a particle, let me say I'll call it 1. And if there are no particles, I will just call it 0. So this way, at any given point of time, I can specify the configuration of the system where I would have a set of zeros and ones, and zeros being signifying that at that particular lattice site, a particle is sitting. That means it is occupied. So for instance, in this case, the lattice site is, this is 1, 2, 3, 4, 5, 6. So the second lattice site is occupied by a particle. The third lattice site is occupied by a particle. The fourth lattice site is empty. Fifth lattice site is empty. Sixth lattice site is empty. And let's say this is also empty. So then your configuration is 0, 1, 1, 0, 0, 0. Okay, this is how I'll discuss. Now in this totally asymmetric exclusion process, you consider such a 1D lattice where particles can be 0 and 1, but you also look at how these particles are moving on this lattice. So what are the rules of moving of the particles? So the rules are the following. So if you, let's say I focus on this particular configurations where you have this, what is of course implied is that they are all sitting at lattice points, and focus on this particular configurations. So if I look at this one with certain rate, this particle can hop to the neighboring lattice site. That rate, let me call it A. So with certain rate, this particle can hop to the neighboring lattice site on the right, provided that lattice site is empty. Okay. So if it hops, if that move is successful, because it is hopping with certain rate. So if I'm looking at certain time, then this is the configuration. Let's say I want to look the configuration at t plus 1. Then with certain rate it can hop, and if that move is successful, remember when I say it hops with certain rate, that means there's certain probability of that event happening. If that event is successful, then your configuration, new configuration becomes like this. Okay. So in this particular model, the particles first of all hop unidirectionally from left to right, and crucially they hop only when the neighboring lattice site is empty, and they do the hopping with certain rate in the bulk, which we will call, let's say, small. Further, I should additionally mention, what about, you might wonder what happens to this particle. So at this, let's say this is some t equal to 20 and this is the next time step t equal to 20. At time t equal to 20, suppose you have a configuration like this, you can ask the question, okay, what happens to this particle which is sitting in the second lattice site? And the answer is that because the next site in this particular configuration is occupied by a particle, then that particle is not able to hop. So the rate of hopping to the site on the right, that is exactly 0. That means it does not hop at all if that neighboring site to the right is occupied by another particle. So at this time step, the particle here will not be able to hop. But again, suppose if I had asked the same question, what happens to this particle sitting at second site? Is it able to hop to the next site? And the answer is yes. Again, it will be able to hop with rate a. That means this particle, with certain probability, can go to the site 3. Why it can go through? Because this site is empty. Okay, and this is as far as the bulk. So how I'll distinguish is, see, this is the first site, second site, third, fourth, fifth, sixth. So the first and the last site I will call are the boundary sites. So that means the boundary sites are I equal to 1, and so this is like the left boundary site. The right boundary site corresponds to I equal to n. In this case, capital N is just 6, but in general, it is some n. Now, the rules at the boundary are the following. So, just let us say you focus on this particular configuration, which I have written here, which is 0, 1, 0, 1, 0, 0. You can ask the question again, what are the rules for the first site? The rules are the following. So, if the first site, that is the boundary site on your left, if that is a vacant site, that means there is no particle sitting here, then at this site, particle from, you just imagine that this lattice is connected to some particle reservoir. So there is a supply of particles from those reservoirs, and you can ask them, then you have to specify is that at what rate it takes, there is a particle input into this lattice that you want to study, and that rate we say is alpha. So with rate alpha, side 0 will become 1. That means whenever there is an addition of particles, then this 0 will become 1, and that happens with the rate alpha. So the first site again gets a supply of particle so long at that first site is empty. Okay. And suppose if I had looked at this configuration where there was already a particle which was sitting on the first site, then you cannot have additional particle which can occupy the first site. In that case, that rate of entry would be 0. And subsequently, of course, once a particle has entered, then I have already told you what are the rules with which it hops on the lattice. That means what are the dynamics of this particle on the lattice. And what I mentioned was that it will exactly have the same dynamics that if it sees that there is a hop with rate A to the next site, etc., etc. If it is that means if the second site is vacant, then if a particle is already there in the first site, it can hop there to the right with rate A. Otherwise, if the second site is occupied, it does not do. So that is the rule of hopping. So what we have now done is specified the dynamics for particles for a bulk site and specified the dynamic rules for the first boundary site on the left. Now, the question that now the specification that I make is what happens to the last site. So what are the rules that I specify? So at the last site, again, the last site is also connected to the reservoir. So consider a configuration like this. So where you have 1, 1, 0, 0, let's say this is also 0, 1. So if there is a particle on the side, that means at site I equal to n, and again imagine that this whole lattice is connected to the reservoir. You say that with certain rate beta, it can leave the lattice. When it leaves the lattice, what I mean is that the last site which was occupied by a particle, and that just becomes 0. So with certain probability, it can leave the lattice, and this configuration 1 will become 0. Okay. So this completely specifies and so obviously if there's no particle, there's nothing to hop out. So then there's no event of particle hopping out of the model happens. So now I have completely specified the initial condition and the rules of the dynamics of the particles on this lattice. And so now we can come to the name, why it's called totally asymmetric exclusion processes. See, notice, unlike in the random walker where there was a probability with which particles could hop to the left or right, here it is totally asymmetric. That means it only always hops only to the right side of the lattice, and that's why it's called totally asymmetric. Why we call exclusion processes? See here, it is concerned, see in random walker, when you are considering what the particle hops to the left or right, it does not care whether there is a particle already sitting on the left side or the right side. Here the dynamics is, it is crucial, and in that sense it is including the fact that it actually cares about what is the occupation of the neighboring side on the right, and that's why in some sense it does not hop, that means it is excluding that side. So you can imagine if it is like, so mentally if you want to have a picture, imagine some hard spheres on moving on a 1D line. So these hard spheres can move to the right with certain rate, but they can hop to the neighboring side on the right only if it has vacant side. If there's already another hard sphere which is sitting on that lattice side, it cannot go. So in that sense, it is taking into account a hardcore repulsion or an exclusion process. So that's why this origin of the name totally asymmetric exclusion process. So these are the rules of the dynamics. Questions we are interested in that we would like to analyze is, first of all, what are the steady state configurations for this particular system? You can imagine that you have some n particles again, this is stochastic process, things are happening randomly, but you are interested in the question. For instance, you might ask the question, what is the distribution of the particles on this 1D lattice? Is it uniform distribution? Is it spatially homogeneous distribution or spatially non-homogeneous distribution? If it is spatially homogeneous distribution, what is the average occupancy of each side? What is the average density, right? That is number one. You can also sort of mentally, you can already sort of get a sense that in this model things are moving, right? In general, from left to right, things would be moving. You're supplying particles, they're going out. You might wonder, so when things are moving, then the question that naturally will occur is, what is sort of the average velocity, or in that sense, the appropriate quantity is, what is the current in this lattice? And is there a steady state current in the lattice? And in that sense, it is very interesting because any equilibrium system that you take, at steady state, the average current, like, particles, gas molecules moving in the room, the average current you're talking about is always zero necessarily. I mean, that's a property of equilibrium steady state. Here you notice in that sense it's also non-equilibrium. Here on an average you will see, in fact when we do the derivation, that there is going to be an average flow of particles from left to right, even in steady state. And in that sense, it will not be an equilibrium steady state. And we will delve more into why it is not an equilibrium steady state. But right now, I want you to at least, before we move in the afternoon when we go on to the derivation, I just want you to first appreciate or understand the statement of the problem, what the rules of the dynamics are, and what is it that we are interested in finding out. And afternoon, we would start with the derivation. How do we go about tackling this problem analytically today? Okay, so I'll stop here. If you have any questions until now, you can of course go ahead. Otherwise, I'll stop the recording. And like I mentioned earlier, we would be meeting today at 2 p.m. today. So tomorrow's lecture, on the usual lecture on Wednesday, stands cancelled. Instead, we would be meeting today from 2 to 3. Yeah, any questions? Okay, so if there are no questions, I'll stop the recording and we would meet at 2 o'clock today.